Hey everyone. So I know radicals have been something that was a little challenging in the review section. Sounds like not necessarily review for everybody. So I'm going to try and really work my way up through these gradually and show you what's going on. And hopefully if you weren't feeling confident about this section when we did it with constants, you'll feel a little better when we get through this. So this is changing the appearance of radicals. And the big idea for this first chunk of examples is it says extract roots, but often this will also just say simplify. That a root is simpler if you make the number underneath it smaller. But again, we can't just like make the number smaller. Say, oh, it's 18, I want it to be 2, and that's smaller. You have to keep the value of your expression the same. It has a numerical value while changing the way it looks. So our biggest tool in this section is going to be the fact that the square root distributes across products. So remember, this is kind of like a PEMDAS thing. If you're only one step apart in order of operations, so think of addition, subtraction, multiplication, multiplication, division being grouped together here. If you are only one step apart, so if you have exponents combined with multiplication, division, they pair really nicely. You can do a lot of rearranging, a lot of simplification, order becomes pretty flexible. Same thing if you have more multiplication and division paired with addition, subtraction. You have the nice distributive property and lots of nice things. When you start getting a couple steps apart, exponents paired with addition, subtraction, that's really tricky. Those don't pair nicely. Simplification gets a lot more challenging. So for multiplication, we can just split the root up. The other thing I would remind you is that the square root of x is the same as x to the 1/2 power, and more generally, the nth root of x is the same thing as x to the 1/n power. And sometimes that can be helpful if you're feeling stuck on these, and I'll just leave you with options of fiddling around with both. Because if you write it in exponent form, you all of a sudden have all your exponent properties open to you, which really this product property is just our exponent property that says if you raise x times y to a power, it's the same thing as raising x to the power, raising y to the power, and multiplying after the fact. So it's basically saying it's allowing you to rearrange order of operations. The top one is written so that the big operation is the power. That's the last thing you would do. The bottom is written so that the big operation is multiplication. It's a product instead of an exponent statement. Okay, so let me get into some of these. First example, this goes back to chapter 1, but I wanted to start with this because it's the exact same process with variables. And as we work through any of this stuff, I hope you're seeing that it's the exact same thing, only there's variables in the mix. So it can look a little scarier, but a big job in an algebra class like this, college algebra, would be to see the simpler problem hidden in the mess. So here I'm saying extract roots or simplify. I want to make the number under the root as small as possible. The only way I have to legally take things out of the root is if I actually apply the square root to whatever I'm taking out. That's not going to help me unless I'm taking out a perfect square. So I am looking for factors of 18 that are perfect squares, and 9 is the one that jumps out at me. So I can split this up into root 9 times root 2, which is the same thing as 3 times the square root of 2. So that product property of radicals, I don't care if you remember to call it that, I'm not even positive that would be an official name, but that's what it is our biggest tool throughout this section. Okay, so let's go ahead and get variables in the mix. That's what we're really going for in this section. Radical expressions with variables. So if I go to this root 75 times x, I'm looking for perfect squares under the square root. And if it helps you to break things down a little more, you can even go all the way down to looking at the prime factorization, and any pair of factors makes a perfect square. So I can look at 75 and say, okay, well that's 25 times 3. And 25 is 5 times 5. So I have 5 times 5 times 3 times x. I can't break x down. X is a variable. That means it could represent any real number unless I'm given some sort of restriction on what those numbers would be. I guess I could say that here I would really hope that it's not a negative number because I'm not supposed to take square roots of negatives. But throughout this section, you should be assuming, unless the problem specifically says otherwise, just assume your variables are positive numbers. I want you to be able to just work with the mechanics of splitting up roots and rearranging roots without getting too tangled in having square roots of negatives and weird stuff happening with that. So looking at this, I can't factor x because I don't know what x is, so it's just its own factor. The only pair I see is 5 times 5. So I'm going to break off 25. I'll write it all as one first. And I can't take the square root of 3 or x, so I'm going to leave them in their own square root. No reason to split them off completely. And then as I separated off the perfect square, I can remove it from the square root by taking its square root. That's the key. The only way to get rid of a square root is with its inverse operation, which is squaring. So if you put a 5 squared underneath it, the square and the square root will cancel each other out. And that would be considered a simplified version of this expression. Again, does it really look that much better? It's just different. But this skill is very important as you move on. You need to be able to manipulate radicals, move things in, move things out. So we want to focus on practicing that. Okay, so moving on to 20 times the square root of x to the 4th. So 20 is not a perfect square, but it does have factors that are perfect squares. So I can say, okay, 20 is 4 times 5. Whoops, 4 times 5. And again, if you can just spot that 4 is your factor, excellent. But I've been talking to some people that are feeling a little bit overwhelmed by simplifying radicals. So I want to show that if you need that really clear, how do I start breaking this down? You can go for prime factorization. And then with the x's, it's x times x times x times x. So you're looking for pairs of factors. When you have a power on your variable, all of a sudden you can break it up into multiple factors. You can't break down the x, but there are 4 of them. So when I'm looking for perfect squares, 2 times 2 gives me a perfect square. X times x gives me a perfect square. And another x times x gives me another perfect square. So this is just one way to look at this. I will walk through this one twice because I want to give you other options. So I'm going to say I have 4 times x squared, and I'm going to save the 5 up and write it last because that's the one thing that's not a perfect square. And then either you can write this out or just mentally split up and start taking the square roots of your perfect squares. So we're going to split up all the perfect squares. And now I can say, okay, the square root of 4 is 2. The square root of x squared is just x. Another one of those square root of x squareds is another x. And then one last step, I'm just going to rewrite that as 2x squared times the square root of 5. I want to point out a couple of things. One is that you don't really have to break x to the 4th down into x squared times x squared. If we're asking ourselves, what would I square to get x to the 4th? I'm hoping that you can start getting pretty comfortable with your powers and say, oh, well, if I had x squared and I squared it, I would get x to the 4th. Another way to look at that is I have x to the 4th square rooted. That means exactly the same as x to the 4th raised to the 1/2 power. And when you raise something with a power to another power, you multiply. 4 times 1/2 is 2. So you can tackle those higher powers on your variables without breaking it all the way down to an x squared. Any even power is going to be a perfect square. So any multiple of 2 works in there. It doesn't just have to be 2. So you don't have to take those in separate chunks, but if it works better, do it that way. Okay, let me erase that so I have room on my next one. Okay, so 24x to the 5th. So again, we're looking for factors that are perfect squares. So I'm going to go back. Hopefully you've seen the factoring trees, the prime factorizations, and can use that if that's helpful to you. I'm going to go back to seeing if I can just pick out a perfect square right off the bat. So I would say 4 is definitely a factor of 24. And generally, that's kind of the way I work through this. Is just, okay, so I know my perfect squares. 2 squared is 4, check for a 4. If that doesn't work, 3 squared is 9, check for a factor of 9. Kind of work your way up through those perfect squares. So having those in mind, if you need to, at first just write off 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Have a little list of those so that you can really get comfortable with knowing a perfect square when you see one. And then for the x's, again, you can go down, I'll write this down at the bottom, and write it all out if you want, and say, okay, here's a perfect square and here's a perfect square. But if you're feeling comfortable with the fact that any even power is going to be a perfect square, you can also just say odd power doesn't work, but if I just split off one of those x's, all of a sudden I know I've got a perfect square. So the 4 and the x to the 4th, I want to separate out. So I'm going to say I have 4 times x to the 4th times 6 times x. You don't have to resort order, but I just like to move the things that I'm going to take the root of out to the front because that's where I generally write them when I'm done. And then we can split up the root. Remember, this only works for multiplication and division. Radicals split over multiplication and division, but not addition and subtraction. When you start to get that far apart on order of operations, things don't work together nicely at all. And then I'm just going to leave the 6x together. You can split them apart if you want to, but then you'll have to mush them back together at the end. So when you've got those factors that you know are not perfect squares, just leave them under a root together, and that will be that remaining piece that you can't do anything with. So when I'm all done, I have a 2. Remember, square root of x to the 4th. Think about it whichever way you want. If you take x squared and square it, you get x to the 4th. Or you can think about this as x to the 4th raised to the 1/2 power. And 4 times 1/2 is 2. So the square root of x to the 4th is x squared. And then the square root of 6x is what it is. I can't really do anything to make it nicer. So that would be considered a simplified answer. Okay, 2 more, and then we'll try some division in the next video. So I've just thrown in a couple of variables in this one. I tried to not actually get too crazy with this. You can find in algebra books, they'll put like 3 or 4 variables with all sorts of powers, and that's fine. We should be able to do that. My thoughts are always at some point you're just making it kind of tedious, and we don't run across lots and lots of variables under roots anywhere up through Calc 2 really, so I think if we can handle a couple of variables, we're in pretty good shape. Okay, so looking at this, 9 is already a perfect square, so I like that. So I don't need to do anything with the 9. So we'll just give it a check. Check. Okay, the x to the 6th is also already a perfect square. Remember I said any even power is going to be a perfect square. So you can think of it again as if I'm taking the square root of x to the 6th, that's the same thing as x to the 6th to the 1/2 power. And you would multiply powers, so you get 6 times 1/2, which is 3. So I'll keep that there because I'll use it in a minute. So that's a perfect square. It's great. 9 is, y to the 9th is not a perfect square. And this one really tricks people because 9 is a perfect square, right? But we're talking about y times y times y times y, 9 of them, right? So ooh, I might hate myself for this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we're grouping together perfect squares, there's 1, there's 1, there's 1, there's 1. We have a y left over. So any odd power will not be a perfect square. That is a perfect cube. You could take the cube root of y to the 9th and you'd get y cubed. But it's not a perfect square. So this is the one I want to break apart. I'm going to break off an even power, and then there'll just be one sad y left over. So I have a square root of 9 times x to the 6th times y to the 8 times y. And definitely if you start feeling comfortable at the beginning of these problems, I feel like I'm writing an extra step in here. I want you to see that so you're really clear, but you can start skipping one of these 2 steps if you would like to. You can go straight to breaking the root up, or you can go straight from this first step I wrote to taking the roots. So totally up to your comfort level. I'm not going to be offended if you forever want to write both of those steps in there. That's great. I care the most about if you're getting through it and understanding, so don't be feeling like you have to do that. Okay, so we split up the product. The square root of 9 is 3. The square root of x to the 6th, we just talked through, is x cubed. Similarly, the square root of y to the 8th is y to the 8th to the 1/2. So y to the 4th, we multiply powers. I can't do anything about the square root of y, so I'm going to leave that, and that is my most simplified answer. Okay, last one. 48 x to the 11 y to the 31. So these numbers sometimes get kind of big. And the bottom line is, it doesn't really matter how big that number is. All that matters is if you're taking a square root, is it divisible by 2? If you're taking a cube root, is it divisible by 3? If you're taking a 4th root, is it divisible by 4? And so on. So here, I can start with the 48. I'm looking for factors of 48 that are divisible by, or that are perfect squares. Got into my divisible talk. So 48, 4 is definitely a factor of 48. But I can actually do better than that because it's also a factor of 12. So I can actually pull out a 16. So I'm going to say, okay, this is the same as the square root of 16 times 3. So I'm going to save that 3 up for a minute. X to the 11 is not a perfect square. If I multiply 11 by 1/2, that doesn't work out nicely. So try to not, it's really easy to get confused. When am I multiplying and when am I not? So when I look at 48, I'm actually taking the square root of 48 because it's just a number sitting there. When I look at x to the 11, I'm not taking the square root of x to the, I'm not taking the square root of 11, I'm taking the square root of x to the 11. So I'm trying to split off a perfect square, and since I don't know what x is, the only way to be sure I have a perfect square is to be sure I have an even power. So I'm going to separate off an x to the 10, and then the same thing with y. I can split off one y, and I'll have 30 left over. So for square roots, all you'd ever have to split off is a single one of your variable. Either the power is even, or you can split off one, and then the power will be odd. Whoa. I see my craziness. If it was bugging you, that should be a y. Okay, so I put the perfect squares out in front. So I'm going to split off a root 16, a root x to the 10, a root y to the 30, and a root xy. And then I can go ahead and take some of those square roots. The square root of 16 is 4. The square root of x to the 10 is x to the 5th. The square root of y to the 30 is y to the 15, and the square root of xy can't be improved on, so we'll just leave it. And again, remember, really one way to think about this anyway is this is x to the 10 raised to the 1/2 power, so the power gets cut in half when you take a square root. It gets divided by 3 if you were going to take a cube root. Okay, so this is extracting roots, simplifying a radical by removing any perfect square factors from underneath it. Thanks for watching.